Hi, and welcome to this video where we'll talk about kinetic molecular theory and its ability to describe and predict the behavior of gases. Before we do that, though, I do want to spend a little bit of time talking about the relationship between a couple of concepts that you might not have thought very much about that before. And the two concepts, which we'll kind of put side by side, are the concepts of a law and a theory. And these two words have very different meanings in science as to other places. So you might hear people use the word theory pejoratively, sort of scoffing at it out in the real world, where they say something like, oh, that's just your theory, meaning that it doesn't have any weight to it. That is not the way we use that word in science. And law and theory turn out to actually be interrelated. So here's how they're related in science. A law's job is to predict behavior. And we're familiar with this idea already, right? We talked about a whole bunch of gas laws just recently. So for example, we had Charles's law, and Charles's law took and related volume and temperature, and it said that if I took a gas at a certain volume and temperature combination and I kept the pressure and the number of moles constant, and then I either heated it up or changed the volume or something like that, the relationship V1 over T1 equals V2 over T2 had to be observed. This is a law. It helps me predict what happens to a gas when I heat it or cool it when pressure and moles are constant. Making predictions is the job of a law. On the other hand, what a theory does is it explains behavior. A theory answers that wait, but why question. So Charles's law says, if I heat up a gas, then it takes up more space. The theory that we're going to talk about today, kinetic molecular theory, says it does that for some certain reasons and some certain assumptions, underlying assumptions that we can make about the behavior of the particles in a gas. And so what we need for any good theory are postulates. So the word is postulates. And what they are is they're a set of unprovable statements. Unprovable doesn't mean bad. Unprovable doesn't mean wrong. Unprovable just means that we don't have some sort of like mathematical underlying thing that says exactly that this has to happen this way all the time. However, without postulates, you can't have a theory. And without a theory, you can't do a good job predicting behavior. Because these two things are actually interrelated. Laws help you predict behavior, so you use laws to develop theory. And then, as you go back and forth, and by the way, the link between these is experiment. We observe laws through experiments, and we use those experiments and those results and those laws to come up with underlying theories. And then, what we do is we push our theory a little bit, and I'll show you how this works in a second, but we prod it and we say, well, if the theory is exactly right, then I would expect this law and this behavior to come out of it. By the way, that's another experiment. And so we're in this constant refining loop. Laws help us develop theories. We refine our theories by predicting what a law would do and observing what comes out. And so it's this constant feedback loop and this constant helpful thing. So let's look at our particular theory now, kinetic molecular theory for describing gas behavior. So again, the theory that we use to describe why gas molecules behave the way they do, why we have an ideal gas law, why we have a Charles's law or a Boyle's law, is called kinetic molecular theory, or KMT for short. It has 5 postulates, and they have to do with, if I could zoom down on a container of gas, and I could see the individual particles in that container, and they could be molecules, they could be atoms, it doesn't matter, but they're individual particles and they're in the gaseous state. There are 5 postulates, 5 assumptions that I could make about their behavior and what they're doing. The first one is about the motion of those particles, and the words that I want to think of are constant, right? Gases are always moving, and so these particles are always going somewhere. The other descriptor that I want you to have in your head of gas motion is that it occurs in straight lines. So a gas moves in a straight line until it hits something. That could be a wall, like I've drawn with my red arrow. It could be another gas particle, like I've drawn with my blue arrow. But the idea is it moves in a straight line until it hits something, at which point it changes direction randomly until it hits something again, and then it keeps going. Constant straight line motion. The only thing that changes, right? The only thing that changes the motion is collisions, and all it does is it breaks off into its own straight line again. The second postulate of kinetic molecular theory that I'd like you to think about is the size of a gas particle. And basically, the size is small compared to the space between particles. So again, if I look at my gas in a container, gas particle over here, gas particle over here, the distance between them is huge, whereas the size of the gas particle is really tiny. And so the implication of that is that the particles take up a negligible amount of space. So if the container has a complete volume of V, I don't have to say, well, wait a second, the particles take up some space and subtract it off. I can just say the container's 2 liters, so the gas is 2 liters. We like that. That makes the ideal gas law really easy to work with. Third postulate is about the origin of pressure. So gas pressure, right, like PV equals nRT, where does it come from? It comes from collisions. And it's between the particles, and I'm going to say PCLs, and the container walls. So we had that straight line motion, and this gas particle moves, and it bonks up against the container wall that exerts a pressure, or force. It bonks up against another container wall and another container wall, and every time it connects with the wall of a container, it exerts a force. And the amount of that force is what we end up calling pressure. That's the third postulate of kinetic molecular theory. The fourth postulate is about collisions again, and it's an assumption that we make about those collisions. Every collision is elastic, right? And what elastic means in this case is that there's no loss of total energy. So when two gas particles hit each other, right, when two gas particles collide, the total energy is constant. They might exchange energy, right? This one might start out at a certain energy and this one might start out at another energy, and they might be different before and after, but the total energy in the container, E1 plus E2, is constant. So, it could have started out with 1 and 3 or 2 and 2, but either way, those both add up to 4. The total energy remains constant. So if you've been keeping track of our postulates up to this point, we have an awful lot about N, right? Because every time we talk about what the particles are doing, we're talking about the N in the gas law. We have a whole postulate just on the P of the gas law, and we have a whole postulate just on the volume of the gas law. So you might be wondering, well, where's my postulate on temperature? And the specific postulate on temperature is this, that if I know something about the average kinetic energy of my gas particles, it's proportional, and I'll show you what I mean by this in a little bit. It's proportional to the gas temperature. This is really just a fancy way of saying that kinetic energy, right, so Ke, if the kinetic energy is up, the temperature is up. And by the way, from physics, we know that kinetic energy equals 1/2 mass times velocity squared. And so velocity is about speed. So it's a fancy way of saying this postulate 5, if kinetic energy is up and temperature is up, the particles must be moving faster as well. Those are underlying assumptions of kinetic molecular theory. I want to talk a little bit more about this average kinetic energy idea, though. One of the truly interesting things about postulate 5 is that it talked about the average kinetic energy, right? It was assuming the average KE is constant. But the average doesn't take into account that in any sample of gas, I've got lots and lots and lots of gas particles. Remember, a mole is 6.02 times 10 to the 23rd gas particles. So even if I have a mole of gas, I have an astronomical, actually past astronomical, an unimaginable number of particles. And what that means is that individual particles, if I was to look at different particles, they can have individual kinetic energies. And because they have different kinetic energies, they have different speeds. And about 150 years ago at this point, Ludwig Boltzmann, who was a Austrian theoretical chemist, he lived in Vienna and taught in Vienna actually, he developed a description of how those speeds were distributed. And this is actually called a Maxwell-Boltzmann distribution curve. So Maxwell was the other guy who was in on this, but Boltzmann is mainly responsible. And so what I'm going to draw for you is called a Maxwell-Boltzmann distribution. And what I've got on the x-axis is a particular speed. And on the y-axis, I have the frequency, right? The number of particles at that speed. And they all look something like this. They all go up and then they tail off slowly. They are not symmetrical. I do want to warn you about that. It's a little bit thicker on the right side than on the left, right? And the average kinetic energy is close to the top of the curve, right? So the way that we would denote that, by the way, is we'd actually say the average speed, and this is proportional to the average kinetic energy. When I put the bar on top, I mean average. And this is slightly different than what we're going to call the root mean square speed, and your book calls it URMS, right? The name is root mean square speed. I'll give you some equations for this in a second, but the idea is this isn't a symmetrical curve. And so it's nice to think about the average, but it's also nice to think about this kind of weighted average, because that's what a root mean square is. It's basically a special kind of weighted average. And you notice that some particles are slow and some particles are fast, and then there's a bunch that are at kind of a maximum most probable frequency. Well, when we turn the temperature up, right, we already said that kinetic energy goes up, and so speed will go up. So what that ends up looking like is something like this. The distribution still stays asymmetrical, but it gets lower and it gets wider. So this one right here is at a higher temperature. T2 is greater than T1. On the other hand, if I turn the temperature down and my kinetic energy goes down and my speed goes down, my distribution gets higher, and it's still asymmetrical, right? This is a T3 being less than T1, and I apologize, this should be a T1 over here on this curve. So there's this distribution of speeds that's important. The last thing that we want to look at, though, is what might happen to predicting some of these things. So we might want to talk about the relationship between kinetic energy and temperature, and also what this root mean square speed is, so we can think about how fast things are moving. The first equation you're going to want to notice is this one that relates kinetic energy to temperature. And you can see our temperature variable right here, and you can see our kinetic energy variable right here. That's another R that we noticed. So this R, this ideal gas constant, shows up in a lot of different places. What I need you to understand is that the temperature must always, always, always be in Kelvin. This equation doesn't work without it, because that R value right here is actually a little bit different than what we're used to, and it has a per Kelvin in it. I'll get to the rest of it in a second, but I want to go back to this kinetic energy, because I want you to know that this comes out in joules per mole. So this is the number of joules of kinetic energy that 1 mole of stuff would have at a certain temperature. And because of that, the R is different. You know, I've got joules over here, and I've got Kelvin and Kelvin, so this R, and also moles, needs a joule per Kelvin times mole. And in fact, that R has a different number. It's 8.314 joules per Kelvin mole. And so you'll need to be able to recognize and use this appropriately. It's not hard. You stick in a kinetic energy, You stick in a temperature, as long as one's in joules and the other's in Kelvin, you're good to go. But this is that relationship. We said kinetic energy was proportional to temperature, and in fact, when kinetic energy goes up, temperature goes up. Let's look at this root mean square speed as well, because it tells us something about how fast molecules will move and helps us make some interesting predictions. The second equation that comes out of the Maxwell-Boltzmann distribution is the idea of relating speed, that's what URMS is, to a couple of parameters about the molecule. Let's look at them. First off, I want you to know that the speed here is always going to come out in meters per second as long as you do everything well, because this R is exactly the same R as before. It's got joules per Kelvin mole, and joules is this compound unit that has meters per second inside it. Your temperature had better also be in Kelvin because of that. And then this third thing is the idea of molar mass. So it matters what molar mass I have. And by the way, that needs to be not in grams per mole, but in kilograms per mole. And it's in order to interface with the R that has joules inside of it. So you just want to be careful that there's this extra thing in it. But what do we notice? I mean, the most important things to see are that if I look at the root mean square speed, if I want to turn it up, looking at the proportionality, I could heat up my sample, right? Heating it up makes the speeds go faster. But the other thing that I could do is use a sample with a lighter molar mass, because the U, RMS, the root mean square speed, is on the numerator and molar mass is on the denominator. So those two things are inversely proportional. So light things move faster. And that fits with some things that we already kind of know. Now that we've talked a little bit about kinetic molecular theory and these postulates, I want to return to the idea of whether a theory is any good. Because just like in regular life, when we use the word theory, it's possible to have good theories and bad theories. And so our test of a good theory, remember we said that laws were for predicting behavior and that theories were for explaining it. And the link between them was an experiment. So the basic idea is that a good theory will predict an experimental outcome. If my theory is right, I can make a prediction about behavior, about laws that I would expect to see. I can go into the lab, I can do the experiment, and if it works the way I predicted, my theory is good. Otherwise, I have two options. One is that my experiment wasn't good and I need to redesign it and fix it. But if I've fixed my experiment over and over and over and I'm certain that that's fine, then I can conclude that my theory is messed up and I have to fix something about it. So kinetic molecular theory is great. It's nice to say that gas molecules move in straight lines, or it's nice to say that the temperature is proportional to the kinetic energy. But if it doesn't help me to predict something about the way a real gas would behave, it's useless and I better fix it. So let's try something. Let's try the relationship between volume and temperature according to kinetic molecular theory. And let's think about what the postulates say, right? The first thing is we're going to assume constant pressure and moles. So that's my first assumption. Before I go to the postulates, we're just going to assume that volume and temperature are the things that can change. So the first thing I want to think of is I want to think of postulate 3. All right? That pressure equals, or is more accurately proportional to, number of collisions. So that means that if I want constant pressure, I need the constant number of collisions. So if in my before picture, at a certain volume and temperature, I have X collisions, my after picture, whatever that V2 and T2 is, had better have the same number of collisions. Here's another postulate I want to think about, postulate 5. That if I increase temperature, I increase kinetic energy. The effect is more collisions. Why? Because a molecule's traveling more distance, and if it's traveling more distance because it's moving faster, it's going to collide more. So if I keep those two things in mind, if I have more collisions happening because the temperature is increasing, but I need a constant number of collisions to maintain the pressure, the prediction is that you can only maintain constant collisions by increasing volume, right? The only way that this happens, if P stays the same and T goes up, V must also go up. That's just another way of saying that V1 over T1 equals V2 over T2. So kinetic molecular theory predicts, right? All I did was start with the postulates, and I was able to predict the existence of Charles's law. And we know from experiment that there is such a thing as Charles's law, and it works exactly like that. So because theory matches reality, right? Experiment is all about reality. When they match, we know that our things are in agreement. It's when they're not in agreement that we have to start fixing.